So in 9.2, called the dot product, we are going to calculate the dot product. We're going to find the angle between two vectors, and then we are going to have a little application that is review from things that we've done earlier in 9.1, and we're going to find what's called the work done on an object. So the definition of the dot product is that if you had two vectors, okay, they call them u and v, then their dot product, denoted by u times v, is going to be equal to a1 times a2 plus b1 times b2. So all that means is you are finding the sum of the products of the horizontal and vertical components. Okay, so you're going to add together, that's the sum of the products of the horizontal, which is the A1 and the A2, and the vertical, which is the B1 and the B2. Okay, I did put the properties of the dot product on here. So you have the commutative property, the associative, distributive. So all of those are going to hold true. And then, yeah, so if you square it, it's the same thing as if you multiply. Okay, and then the angle between two vectors. This is something else we're going to use. So if you're trying to find the angle between two vectors, okay, it says it has to be the angle between two non-zero vectors, then the cosine of theta is equal to, and that is the dot product on the top. Okay, and on the bottom, that is the product of, remember what the absolute value means. The absolute value means you're finding the what? The magnitude. Okay, so for example 1, we're going to find the dot product and the angle between to the nearest degree. Okay, so we're going to round each one to the nearest degree. Okay, so here's our vector. Our vector u is 3, -5. Our vector v is 1, 4. Okay, so when you're finding the dot product, this is how we write it. U and then times v. Okay, so we're just going to multiply the horizontal component. So 3 times 1 plus -5 times 4. Okay, so 3 minus 20, -17. All right, and then for step 2, we are going to find the angle in between these two vectors. Okay, so you have the cosine of theta equals the dot product over the product of the magnitudes. Okay, so we already found the dot product. You have -17 on the top. Okay, now we're going to have to find the magnitudes for each one. Okay, so we're just going to do the square root of 3 squared plus negative 5 squared. Okay, so the magnitude of u is the square root of 34. And then we're going to find the magnitude of v. Okay, so 1 squared plus 4 squared would be root 17. Okay, so in order to calculate this, if you have the cosine of theta equal to this value, that means theta is equal to the cosine inverse of negative 17 over root 34 times root 17. Okay, and you guys need to practice this on your calculator because depending on what you have, you might have to put some different parentheses in there. So square root of 34 times, and actually you could put those underneath the same radical. That would be fine. Let's see if I can do this without this set of parentheses. Let's see. Oh, yep. See, you get an error. Yep. All right. Can't use that one. But you can put it in those parentheses. So it says to round to the nearest degree, but this gives this to you to the nearest degree, so you're all set. All right, so I'm going to have you do B, and then we'll check that together. Okay, so for you, you have 4i plus j. And for vector v, you have 6i minus 5j. All right, so I'm going to give you a couple minutes to do that now. Check and see how we did. All right, so Lily, what'd you get for your dot product? Great. Okay, do you guys have any questions on dot product of 19? All right, and then for step 2, you are using your dot product. So you have the cosine of 19 should be in the numerator, and you're finding the magnitude of each. Okay, Olivia, what'd you get for your magnitude of vector v? Yep. All right, and then Brady, what'd you get for your magnitude of u? Great. And then, Maya, what'd you get for your value of theta? Okay. Just whenever you got it, let me know. Okay, so you were doing the inverse here. Yep, and then we're going to round that to ... So then we're going to round that up. So you guys should have 54 degrees, the nearest degree. Okay, great. All right. The next thing we're going to talk about is an extension of the dot product. It says determine whether the given vectors are perpendicular. Okay, so remember, if they are perpendicular, they form those 90-degree angles, right? Remember that from geometry? Okay, so we have a rule that says two non-zero vectors are perpendicular if and only if their dot product is equal to 0. Okay, so two non-zero vectors are perpendicular if and only if their dot product is equal to 0. Okay, and we're going to think about why the dot product has to be 0. Okay, so we just learned how to calculate the angle in between the vectors. If you calculate the angle in between the vectors using the cosine of theta equals the dot product over the magnitudes, okay, if 0 is the dot product, you have to find where the cosine of theta equals 0. Think of the unit circle. If the cosine of theta is equal to 0, your theta is going to be what? What's your angle measure if your cosine 0? 90. Okay, so why does the dot product have to be 0? Because to be perpendicular, we'll use the symbol. There must be a 90-degree angle. And the cosine of 90 is what equals 0. Okay, so that's how you can tell if they're perpendicular without having to calculate that cosine inverse. Okay, so you are going to have to know that terminology, okay, that if they're perpendicular, their dot product is 0. Okay, so you'll be given two vectors, and then you just have to calculate the dot product. If it's 0, they're perpendicular. If it's not 0, then they are not. Okay, so the dot product, multiply the horizontal, multiply the vertical, and add them together. Okay, so 12 minus 12 is 0. Okay, if you get 0, the answer is yes. You guys with me? Okay, so you could be given a vector in vector form or component form with INJ. But your process is the same. Okay, and I know I've been writing out this step a lot. It's fine when you're doing your own work. If you just want to write -9 plus whatever, that's fine. Okay, you don't have to do the first step, but you do need to show how you're getting there. Okay, and then if it's not equal to 0, not perpendicular. Thank you. Okay, so since the dot product is not 0, they're not perpendicular. All right, and then in example 3, we are going to find, so v times u plus v, okay, and you're given u, v, and w, or v times u plus w, I don't think I said that right. Okay, so you have vector u, vector v, vector w, and then we do have to follow the order of operations here. Okay, and when you see that dot there, that does mean the dot product, okay? Okay, so if you follow the order of operations, you want to do what's inside the parentheses first. You don't have to do this. I like to write these out in vector form. It's just easier for me to process. If you like to do that too, you can. Those are your vectors. Okay, so if you do v times, and then the u plus the w, okay, you can just add the 2 and the 3 to get 5. You add the 1 and the 4 to get 5. Okay, so u plus w is 5, 5. Now you're going to do the dot product. Okay, so to do the dot product, vector v is 1, -3, dot product of 5, 5. So you do 1 times 5 plus -3 times 5. Okay, if you wanted to, remember how we talked about how the distributive properties hold true? You could also do v dot product of u plus v dot product of w. Okay, and if you did that, you'd have 2 plus -3, which would end up being -1, and you'd have 3 minus 12, which would end up being -9, and you would still get -10. Okay, so you can distribute, or you can do the parentheses and then the dot product. All right, let's talk about some work. We are going to calculate work, which is the amount of effort required to perform a task. Okay, and this is one of the uses of the dot product. So in everyday use, your work means, like I said, the total amount of effort required to perform a task. In physics, work has a technical meaning that conforms to that intuitive meaning. So if a constant force of magnitude F moves an object through a distance d along a straight line, then the work done on an object is given by the following. Okay, so work is equal to the force and the distance and calculating their dot product. Okay, so you would just see this as W equals FD. Okay, so sometimes they're going to give you the vector. It says the force is given by the vector F, and it moves an object from the point 2, 1 to the point 5, 6. So you have to calculate that vector. Okay, this is the initial point. This is the terminal point. Okay, and then we have to find the work done. So all you need is the force vector and the distance vector. You have the force vector, you have to find the distance vector. Okay, so the way that you find the distance vector is going to be the terminal point minus the initial point, which is what we did the very first day of 9-1, which I know feels like a long time ago. Okay, so your initial point, this is your x1, y1. Your terminal point, this is your x2, y2. Okay, so the distance vector is going to be 5 minus 2, 6 minus 1. Okay, so 3, 5. You could also plot those on a grid and calculate that vector. Okay, it would be going right 3 and up 5. That would be another way that you could do that. Okay, the force vector is already given to us. It's 7, 6. And then we just have to calculate the work. Okay, so the work is going to be your dot product. So 7 times 3 plus 6 times 5. Okay, so 7 times 3 is the horizontal, 6 times 5 is going to be the vertical, 21 plus 30 is going to be 51. Okay, and in this case, it doesn't give you units. We are going to do one that has the units on it. So in example 5, a man is pulling a wagon horizontally by exerting a force of 30 pounds on the handle. If the handle makes an angle of 70 degrees with the horizontal, you are going to find the work done in moving the wagon 200 feet. Okay, so in this one, we're going to find the force first. Okay, so a man is pulling a wagon. Here's my handle. Why is he flying? I don't know. This is now his shirt and his pants. Sorry. All right, so this is the wagon that he's pulling. All right, and then you know the force is going to be 30. Okay, and then it says the angle it makes with the horizontal is 70 degrees. Okay, so what we're going to have to do is use our components like we have been. Okay, so your force vector, you can see it doesn't matter what order you find these in, is going to be the force times the cosine of your angle and the force times the sine of your angle. Okay, so you're going to calculate that using your calculator in degree mode. Okay, so we're going to do 30, cosine of 70, and 30, sine of 70. Okay, and you can just round to the nearest hundredth like we have been. Okay, so that's your force factor. For the distance factor, okay, you are moving 200 feet. Okay, so you can think of this as you start at 0, 0, you move 200 feet, right? You're going to be going in a vector this way, right? How would we say the name of that vector? It would just be, yeah, 200 minus 0, and then 0 minus 0, right? So it's just 200, 0. You're going 200 feet horizontally, right? So this is your horizontal component. You're not going up, right? He's not flying, even though he looked like it for a second. Okay, so if you're calculating that, it can just be the length and then 0. That's your vector. Okay, so then when you're calculating the work, which is just the dot product between the force and the distance, okay, you're going to have that 10.26, 28.19, dot product 200, 0. When you're calculating this, you know if you multiply by 0, you're just going to get 0, right? Okay, so we can just multiply by 200. Okay, and whether you take the rounded answer or the exact answer, you are going to round to 2,052. Now, see how the force is pounds and then you're moving feet? This unit is called foot-pounds. Okay, so the work done for a distance of 200 feet when you have a force of 30 pounds, 2,052 foot-pounds. Okay, so it might be pulling that wagon on the sand. Some has kids in there. All right, so I'm going to show you what your assignment is for tonight.